In 1D motion, we discussed a lot of very basic concepts such as displacement, time, average velocity, instantaneous velocity, average acceleration, instantaneous acceleration, etc. So all these concepts, I think the important ones that can be tested, such as average velocity. So say average. So average velocity, this is very apparently not equal to, say, velocity 1 plus velocity 2 divided by 2. That's not average velocity. That is the average of two values. Average velocity, this V average, is defined as x2 minus x1 over t2 minus t1. So you know the displacement, you know the time duration, you can get an average velocity. So just averaging the velocity values 1 and 2 does not give you a good description of the average that what is happening, because you could have a velocity that is going on for a long period of time, covering a long distance, and then another velocity that only happens for a very short period of time. And if you average the two, you don't really get a good description of the motion. Okay, so the same thing happens for average acceleration. So if you have a acceleration average is velocity 2 minus velocity 1 divided by time 2 over minus time 1. Okay. Okay, so the next subject we can review is instantaneous velocity, how these things are connected. This is v as a function of time is d position over d time, and acceleration as a function of time is d velocity over d time. So we could do some derivatives, or at least to test the competency of derivatives. So I'll give you an example, such as x function of time equals maybe 2x cubed, not t cubed minus 4t squared plus a5. Okay, so that's just a made up position, how the position depends on time. So how do we get velocity? So velocity is dx over dt. So that's d over dt, 2t cubed minus 4t squared plus 5. So cube differentiates into the 3 drops out, multiplied by 2 is a 6t squared. And the 2 drops out, multiplies the 4, gets you 8t. And then the constant derivative is 0, so plus 0. So that is our velocity. And acceleration is another derivative, d velocity over dt. So that is differentiate this over t, the 2 drops out times 6, 12t, and minus 8. So I could ask you a question, for example, say, question is, where and how fast is the object when it has 0 acceleration? Okay, so how do you answer that question? Well, having 0 acceleration means you need the acceleration expression, such as this one. So having 0 means acceleration is equal to 0, or 12t minus 8 is equal to 0. So you can solve for t. T is going to be 8 over 12. So 2/3. Right, let's keep it at 2/3. And the where and how fast will be asking. The where is this. If you plug in t equal to 2/3, you get 2/3. So 2 times cube of that, 8. 27 minus 4 times 4/9 plus 5. So that's whatever number. And how fast will be velocity at 2/3 seconds. So that is 6 times 4/9 minus 8 times 2/3. So that's whatever value that is. So a question could be posed as this: instead of just asking you for what is the velocity or differentiate until you get acceleration, instead it will ask you when something is equal to something. That means this something could be acceleration. So you have to find the acceleration using differentiation, and then whatever you want your acceleration to be, you equate that number with this expression, such as 0 equal to this expression. You can solve for the time. So once you have the time, you can put back into the position or velocity depending on what you're asked. Okay, so the next subject to review is motion with constant acceleration. So constant acceleration motion. We have two formulas. One is how the position changes with time. So initial position plus initial velocity time. See, if we just stopped here, this is the constant velocity motion with 0 acceleration, which is also a constant acceleration motion, a constant 0, right? Plus 1/2 at squared. And velocity is velocity 0 plus acceleration time. So the 1/2 here, since we were reviewing with calculus, 1/2 actually comes from taking derivative. If you take derivative, this x with respect to t, x should go into a v, and this left side, the constant is gone, this is gone, turn into that, and this 2 drops out, cancel 1/2, gets you at, just the same as that, right? So these two are related together with differentiation. With these two equations, we can solve a lot of problems. So example problems could involve, say, an airplane landing on tarmac, maybe a drag race car starting from the starting point to the finish point, or anything that accelerates with a constant acceleration, maybe a rocket being propelled, or some machine being accelerated. So I'll give you a very quick example of, say, a car advertisement. So a car goes 0 to 26.8 meters per second in, say, 5.5 seconds. Okay, so this is actually the 60. That's why I said it was in car advertisement. So that's the 0 to 60 in 5.5 seconds, except that I promise you not to give you any non-standard units. So So this is just a statement of fact, and we want to know how far. Basically, how far does the car travel in the 5.5 seconds? And we can calculate this. We can also, we can ask for acceleration, but that's pretty obvious. So let's just ask for how far. We'll use these two equations, although it's not necessary to use the full-fledged equations. We'll just show how we use them. So we start with a list of parameters: x0, x, v0, v, a, and t. So let's draw a very simple diagram. So we have a horizontal axis that points to the right, origin right here, and we'll put the car right here at the origin, and accelerates all the way until it gets here when it's actually moving at 26.8 meters per second. And this position, let's just do the rear bumper. So this position, what is it, right? So this is x. This is x0, which is lined up with the origin, and the v0 is a 0. So now we can put 0 meters, and we don't know that initially at rest finally reaches 26.8 meters, and acceleration, let's say we don't know that, although it's easy to calculate, and times 5.5. So we just want this list. Once we have the list, we can plug in the numbers. The equation 1 with position, so x equals 0 plus 0t plus 0.5a t squared, 5.5 squared. Okay. So this is equal to, let's use Python. So 0.5 times 5.5 squared. So we have 15, 125, let's just do 15.1. So we have 15.1a. Okay, and according to equation 2, 26.8 equals 0 plus a times 5.5. So a is equal to 26.8 over 5.5, which is, according to our Python, so we have 4.87. Since we're still using Python right here, we can do 4.87 times the 15.1, the previous step, to get the total distance, 73.5. Okay, so 487, 73.5. And then x (73.5). So let's put the units in. We'll move this a little further down. Ooh, it's interesting. Now I have space for the unit. Okay, so that's how you would use a constant acceleration motion, basically using the formula and enumerate all these factors. Try to find out. Sometimes there's hidden factors, such as going from 0 to 26. That's an initial velocity, and starting from rest, or things like that. You can be used as numerical values. Okay. So the next one we want to review is free fall. Free fall is constant motion, constant acceleration motion with a constant acceleration that is negative 9.8. So we replace a with minus g, and we usually point our axis upward, so the g downward is a negative acceleration. So we have this formula: initial position, initial velocity times time minus 1/2 gt squared, and velocity is initial velocity minus gt. Okay, so an example would be, say if you toss an object up and watch it fall down, maybe toss an object down, or something just falls off the edge of a table, and you only are concerned about the vertical motion. So things like that. And you can also do something such as free fall on a different planet, on the moon, just not in outer space, because there's no g. So we'll have an example here. So let's say tossing a ball upward at say 7.5 meters per second. And let's see, we're tossing it upward, so probably 1.5 meters above ground. Okay, so we're interested in a few things such as how high. How high will it go? And how long till it hits the ground? And how fast when it hits the ground? I said at ground level, that's because there's a confusion. Sometimes students will say, well, it hits the ground, it's zero because stop. No, that's not the part of free fall anymore. So when it's at the ground level, about to hit the ground, just imagine there's a big hole there. The ball will never hit the ground because of the hole, but it does pass through the ground level. So how fast is it when it's actually entering that hole at the ground level? So that gives you a clarity that the ball never hit anything, so it's still in free fall motion. It's not zero. So we'll use the same procedure. We'll have this list here, except that the acceleration has been figured out, has been specified as 9.8 with the negative already explicit. So the g is always positive 9.8 now. Okay, so let's do a list of parameters. X equals, x0 equals, x equals, v0 equals, and v equals. Now we can jump to t equals. Okay, so we want a diagram. So let's keep the diagram on the right side. We have enough space. So let's say here's the 1.5 meters. And we toss the ball, it goes up and comes down and hits the ground, something like that. So here we have heights that need axes an axis to describe. Since there's a ground, I normally would take the ground as 0. This is 1.5. This is, well, the x. So we use x-axis, although in 2D we'll use y for vertical. So this is what happens. It just goes up here to the x and then comes back down through that 1.5 down to the ground. Right? So this is one continuous motion, but we're asked about how high. So how high means what is this x value when it stops moving? Okay, so this is what is x when v is 0. So that is the expansion to the high, how high, that question. So we'll put the 1.5 in here, and x is unknown height. Initial is upward, so 7.5. And final velocity is 0 when it gets to that point. And the time, we don't know how quickly it gets there. Although we're not asked, we can solve it. So we'll still use a long route using this. There's also a short route because we don't really need the time. We could use another formula. So let's use the standard formulas first. We'll plug in the numbers. X equals 1.5 plus 7.5t minus 4.9. Let's just use 4.9. It's okay. Okay, so t squared. All right, and we have the velocity one. The velocity one is 0 equals 7.5 minus 9.8 t. So from here we can calculate t out. So t is equal to 7.5 over 9.8. So it's a fraction of a second. It stops. Let's use Python. So 7.5 over 9.8. So we got 0.765 seconds. And then we can plug this into the first equation. Let's draw that. Plug it in here, also here. So we have 1.5 plus 7.5 times 0.765 minus 4.9 times 0.765 squared. So we can find the maximum height. Let's use Python again. Since we have the 765, we can use underscore to recall this value. And I'll type up the rest. So 1.5 plus 7.5 times this underscore, the previous value, minus 4.9 times the previous value raised to the power 2. So 4.337. So my diagram is not really to scale, but that's okay. We're just trying to draw just a concept. So 4.37. This is measured from the ground, right? So this is 4.37. Okay, so the next step, how long till it hits the ground? So let's just say starting from it was tossed, so the total time, right? And then how fast. So we should have the same exact starting point right here, or you want to move your starting point over there. It's your choice. I usually just don't change the starting point. I'll still have the same x0, v0 right here. If you change it over here, that works too. So let's have the second part calculated. So x0 equals x equals v0 equals v equals and t equals. Okay, so if you do move your starting point to this point, then the t is since this point in time. And watch out for the exact question, how long since when it's tossed, and then you have to add back this point, this time, to this, if you do move your starting point over here, because that will no longer include the upward time. So I'd rather just keep it from here. So off the hand that tossed it, so 1/2. And landing on the ground, at ground level, 0 height, and initial velocity 7.5, final velocity striking the ground, no time was known. So we'll do the same thing, 0 equals 1.5 plus 7.5 t minus 4.9 t squared. Now we have a full-fledged quadratic equation. So hopefully you have your quadratic formula handy. We'll solve it. We have t equals 1 over 2a, so minus 9.8, and then minus b, minus 7.5, plus minus the square root of 4a, b squared minus 4ac, so 75 squared minus 4 times 4.9 is a negative, so turn that negative to positive, times c, 1.5. So there are two roots. One of them is a positive time. The other, I suppose, is negative time. And we'll just keep the positive time because this time has to be beyond the starting point of 0 and when the ball lands. So let me use Python to calculate. I think I already have a function here that I wrote. Quadratic, is that? Let me take a look at the name of the function. Okay, spell it out. Okay. Okay, I'll be asked for A. The A is minus 4.9, and B is 7.5. and C is 1.5. So now I should be able to get two numbers. Okay, so minus 0.179 and a positive 1.71. 179, 171. So don't use that, use this one. Okay, now I have the solution. I can take it to the second equation. This is already one of the answers is how long till it hits the ground, and how fast. I can use the second equation, the v equals v0, 7.5 minus 9.8 times total time 1.71. So use Python again. I already have the T2 defined, so I can use that T2. So 7.5 minus 9.8 times T2, I believe. There we go. So it's a negative quantity. That makes sense. The velocity points downward, right? It's hitting the ground. 9.25 negative. Okay, so this concludes our review of the one-dimensional motion. Thank you.